All right, we're going to look at the physicality of our diode here, and that's going to play out when we look at our transistor in the next video. So the simple way we tend to draw a diode is something like this. So we have a P material and an N material, and we'll talk about that in just a second. And we know diode has two leads, and so we'll indicate those as metal, so that blue is a metal. And we have our anode and our cathode. And as we look at this, we do plus to minus, anode to cathode. There's our diode voltage, and current flows from the anode to the cathode. There's our diode current. And when we model this, we model it, or lay it out in a schematic, I should say. There's our schematic. We're familiar with that. We've seen that. And again, here's our plus, our minus, our anode, and our cathode, and current flowing from the anode to the cathode. Now, just getting into the physics here, diodes are constructed of silicon. And silicon has 4 electrons in the outer shell. And maybe you've learned this in one of your other classes, and maybe in more detail. This is kind of the Cliff Notes version. And if we have 4 electrons in the outer shell, then silicon can form a nice crystal lattice with 8 electrons shared. In the outer shell. So each silicon atom shares with another silicon atom. Double bar means there's 2 electrons between. So if each one contributes 1 electron to the other atom, we have 2 electrons shared between, and we can repeat this. So that's one section. We could do more and continue that on. And there is our basic silicon layout. A nice rectangular crystalline structure that we see on the schematic or on the iPad here. When we look at the P and the N type, so we have our P material, and that means we have a dopant replacing an electron. And something like boron, which only has, I don't need the parentheses, oops, a little bit bigger erase than we needed, which has 3 electrons in the outer shell. And so it's missing one. And the absence of an electron the missing electron is a hole, which effectively has a plus charge. So a P material is a material that has a net positive charge. And holes are essentially missing electrons, but holes can move because that electron in the neighboring atom can go and move into the hole, creating a hole in the neighboring atom. So holes effectively move. We have our N material. And again, we have a dopant replacing an electron, so I can repeat that. And dopant can be something like phosphorus. So we have a very similar setup. But phosphorus has 5 electrons in the outer shell. Well, I never wrote shell up there. And so we now have an extra electron kind of ready to move. The extra electron is a negative charge. And that can move. So it's not tightly bound with any of our atoms ready to move. So P material is a missing electron creating holes that are ready to move. An N material is an extra electron that's ready to move. So as such, if I go and redraw that, here's our PN material. And we have our contacts at the end. Oops. And essentially, in our hole material, we have a bunch of positive holes floating around. And in our N material, we have a bunch of electrons floating around. And the electrons move that way at the border, and the holes move that way. This is diffusion. It's, again, kind of a classical model, so to get into more detail, you have to look at the quantum mechanics. But when the electrons in the holes at the boundary between the PN material move, they create a depletion region. And so all those electrons in holes kind of go away and replace it with a net charge. So there's a depletion region here. And so this becomes a depletion region. And a depletion region is a non-conducting region. If we have holes and electrons just freely ready to move, it's a conducting material. But the depletion region has no holes or electrons, so it's non-conducting, and no current can flow. So the green here, just to label it, is electron diffusion. It's not current. Just be careful with our arrows. And the hole in the blue is hole diffusion. If we apply a voltage, plus minus, if we apply a voltage across our diode from the anode to the cathode, then we can force those charge carriers back into the depletion region. Across the diode, positive voltage. If we apply a negative voltage, the depletion region gets bigger, and so that's kind of important. That gets more off, you could say. Across the diode, charge carriers move back into the depletion region. When I say charge carriers, I mean holes and electrons. And the diode turns on. And I suppose I should be careful. And once we reach a threshold, or a turn-on voltage, the diode turns on and current flows. And current flows. Now, to be a little bit careful here, we don't actually hook a voltage source up directly to the diode. That's not safe. We could exceed the diode's rating and burn it out. So we would normally have a more complicated circuit, namely a series resistor in series with the diode, as we saw in the lab. So that said, come on. I don't know why my little button here is not working. All right. Cliff Notes or Good Notes is crashing out on me. Every now and then it does that. So let's restart it. There we go. All right. So that said, for our 1N914, the turn on is somewhere in the 0.6 to 0.7 volt range. So there's the parameter, and we can go look at that. And I did grab the spec sheets, so these are spec sheets you have available to us. It's the forward voltage. We're looking at this parameter here, the forward voltage. What's interesting a little bit here is it doesn't give the typical value, it gives the maximum value. In one of the homework problems, I asked you to look and see if that maximum value is a realistic value when we consider our diode, and most likely if you applied 1 volt across the diode, it wouldn't work right. It would not work as expected, I should say. So that's a little bit of an extreme reporting, I think they just said this is the max value, but typically here, we're looking at 0.6 to 0.7. So there is our typical forward voltage when the diode is on. That's an important consideration. Here we're talking about current flowing. So in our little parameter here, we have 10 milliamps. In order to get 10 milliamps from the diode has to be, or to have 10 milliamps flowing, the diode has to be on, and then we're in the 0.6 to 0.7 volt range. Another parameter that is of interest here is our forward current. So they didn't actually put these on the same pages, but we can look at the diode current, and this is kind of a peak value. So they have the absolute maximum rating, so around 300 milliamps for our 1N914. There are diodes that allow much, much larger current. There are diodes with less current as well. So there's our maximum forward current. That's the safest, presumably the safest current. There's other parameters that would affect that, and we'll talk about that when we look at the diode equation in an upcoming video. So there's our brief discussion of our physics. We can add a little note here. Maximum forward current for our 1N914 is around 300 milliamps. That's the reported value. And maybe you can go larger than that, or maybe it would be less than that. But anyway, there's a little bit of a discussion of our diode physics. And again, you can get this in a lot more detail in a class that is dedicated to this. So that was the Cliff Notes version. And we'll carry this forward to talk about transistor physics as well. So close that video. At least I'll try to close it. There we go.